All right, this week we're going to start talking about pressure. What is air pressure? So we got to first figure out what that is, and then why is that important in meteorology? And it really is very. So let's define it. We're going to talk about what's called a force. You ever push on something? You ever watch somebody hit someone? Well, believe it or not, that's a force. That is applying pressure to somebody. Literally, pressure is a type of force. When you push a mass, which is amount of weight, or not really weight, but a lot of molecules, for example, and give them an acceleration, if there's a lot of molecules in a piece of metal or a baseball bat, we'll say, when you're swinging that bat, you're accelerating it forward. That is a lot of force you're applying, and that's what you're hitting the baseball with. All that force on the baseball bat, or when you're kicking a soccer ball from your leg. Air molecules move. They're always in motion. They're random. And because of that, they exert a pressure on the surfaces around them. So with that, that means that there's a law that says each type of gas exerts a pressure. If I have carbon dioxide, if I have oxygen, if I have nitrogen, all of those gases in the atmosphere exert a pressure. And the total of each one of those individual ones is the air pressure at your location. It's a force. So it depends first on the amount of molecules you have, and then secondly, on the kinetic energy of those molecules. So in other words, if I have a lot of molecules compressed together in one area, and then apply something to make the kinetic energy faster, and we've learned kinetic energy is related to temperature, so the higher the temperature, the faster those molecules are moving, that's going to make an air pressure, right? Well, which one is going to outweigh the other? Is the number of molecules going to be more important, or is the kinetic energy going to be more important from the heating? And that is something that works out in meteorology. You've got to figure that out. It varies from location to location and different things. So average air pressure is 14.7 pounds per square inch. So every one of you and every square inch of your body is weighted down by 14.7 pounds. That is the weight of the air. How do we measure it? We use a barometer. And there are different types of barometers. We used to use mercury barometers all the time. We don't anymore because we've learned mercury is not a good substance. It's actually very harmful. So things like pulling the air down, all that weight above you is pulled down onto you. And if I take an empty tube, fill it with water or mercury or something to the very top, have a pool below it, seal that tube, then stick it in it, that water pool or mercury pool, it's going to come down only so far because that is the weight of the air pushing upwards in that tube. It will hold that substance up. When we measure that in heights, that's how we got inches of mercury, that is the weight of the atmosphere. And it varies. It varies depending on your elevation. It varies on the type of air mass you have over you. I like to use millibars because mathematically equations in meteorology are a lot simpler. But you can also do it in inches of mercury. So you can see a table here that just converts these. Interestingly, air is compressible. So I can pack air together. I do it every day in my tires. When I'm driving in my car, there's air pressure in those tires that's greater than the pressure out in the atmosphere. That's because I pushed air into those tires. So air is compressible. They're in that tiny little space of my tire, and I keep putting more pressure in. If you have bicycle tires, Some of those can be really pressurized to a lot. And that is because air has been pushed in. It compacts. Other fluids don't necessarily compact. One of them that does not is water. So when you look at water out there in the ocean, if I'm pushing my hands together, it's just going to spray in all directions, which makes it a lot of fun sometimes, but by the same token, it's not compressible. So now that we know air is compressible and we know it's going to drop with height because there's less molecules the higher up you go in the atmosphere. We've already learned that. So as we go up on top of a mountain or go up in an airplane, the air pressure is going to continually get lower because there's less mass. It doesn't mean the molecules are moving less. If I kept the temperatures the same all the way up, but dropped the number of molecules, the pressure is still going to drop. And through the years, we've actually calculated a standard atmosphere. What that means is we've looked at vertical profiles of the atmosphere and averaged them over time for every latitude, every season. That is a standard atmosphere. Believe it or not, the atmosphere is almost never standard, but we've got to start somewhere. We take an average. Horizontal changes in air pressure are usually accompanied by weather. Most of the time when the pressure rises, fair weather is coming your way. Most of the time when pressure falls, bad weather is coming your way. We're going to look at some of that here in a minute. So I know if I heat something that's in a container, it's going to exert more and more pressure. The pressure is going to go up. However, I'm in the atmosphere. Guess what? I heat a volume of air in the atmosphere. What's going to happen to those molecules? Well, the air is compressible, right? So it's going to push those molecules apart to somewhere else. So I wind up with not increasing the pressure at all. I just spread the molecules out over more area. So interestingly, cold air is denser because it has more molecules there. Even though it has less kinetic energy, the molecules are closer together. So if I went in the vertical, climbed up a mountain in a very cold air mass, the pressure is going to drop faster. If I had a very hot, muggy day, the pressure is going to drop slower. That's important. You're going to see that over and over in meteorology. And interestingly, air is less dense when it has a lot of water in it. So, every time when I used to watch baseball, and I still do watch baseball, the announcer tells me, boy, is it hot and humid today. That air ball's not going to fly that far. Well, guess what? He's wrong. And statistics actually prove him wrong. But there is a lot. The air is hot, so we push the molecules apart. There's less molecules. There's a lot more humidity, water in the air. Oh, guess what? Water weighs less than normal air, so it's actually even less dense. So the two combine to make the air actually less dense. It feels ridiculously muggy and hot. It feels heavy, but it's not. So air moves all over the place. Winds move the air. So if I'm pushing air together, I'm converging winds. They're converging, meaning coming towards each other. So I am pushing the air together. That air is going to start compressing. At some point, it's going to have to move, though. It's not going to want to stay in that little tiny area. So when it does, if that convergence is happening, say 5,000, 10,000, 15,000 feet up, where's the air going to go? It's going to tend to come down more than go up. Now, if I am doing the opposite, pulling away, the same is going to happen. If the air is pulling away above you, the air below you is going to want to go up to that higher elevation. So there's something called the ideal gas law. All it's saying is pressure and temperature and density are proportional to each other. So if I know 2 out of the 3, I know the third. So there is something called air doing work. if air expands, it's pushing apart. So it's actually doing work. It's releasing energy. So when it's doing that, the temperature is dropping. When I'm pushing it together, work is being applied to the air. It's gaining energy. Temperature is rising. That's why when you release, as it says here, release air from a tire, it's cool air. It gets cooler. Or when you're pumping the tire up, it gets hotter. Guess what? The same thing happens in the atmosphere. So as an air is going upwards, it's expanding because it's less and less air is above it. It's going to cool. When it's coming downwards, it's going to warm. And you can see that being there. So with that in mind, I can actually calculate how fast the air temperature is going to drop if it's dry air. So if I went up 1,000 feet, the temperature should drop 5.5 degrees Fahrenheit, or 9.8 Celsius per 1,000 meters. That is called the dry adiabatic lapse rate. That is how fast the air temperature drops. The atmosphere is not normally in dry adiabatic lapse rate because other things are going on. But if I had a perfectly dry atmosphere, that would be what you would look at. If you plotted the temperature in the vertical, that would be how fast the temperature would change for every feet. Moist adiabatic is different. Condensation occurs. We know that condensation releases heat. We learned that in the last chapter. So when you get that applies a little bit of heat to it, so the air is not going to cool as fast. So where you have clouds, temperatures aren't cooling as fast. So that can make for some interesting things going on in the atmosphere with time. But with that, I just wanted to show you this is a current temperature map. I can get up here a minute. This is a graphic. Relative humidity, temperature, and pressure. Let's select pressure here. We'll do sea level pressure. I want you to notice this is Mansfield, Ohio. Pressure had been dropping until yesterday afternoon. Now it's been rising after that. Well, what happened was a cold front went through you all. So when it went through, pressures dropped as that front approached and went by. When you have a front, pressures are lower. I also wanted to emphasize this fact of air pressure dropping when very cold air. The coldest air right now in the United States is over the Great Lakes. These are thickness lines. In other words, it says, okay, if the pressure if the surface is this high, how high is 500 millibars? That's a thickness. And notice where it's coldest, the thickness is lowest. So we know that pressure drops faster in the vertical. This is a perfect example of that. So the colder the air, the faster the pressure is going to drop in the vertical. The lower the 500 millibar surface is going to be, the lower the 300 millibar surface is going to be. So that is your introduction to air pressure. So when a cold front is coming at you or a low pressure system is coming at you, pressures tend to drop. Bad weather might probably follow. A lot of times when high pressure is coming at you and pressures are rising, good weather is coming your direction. Take a look at it this week and see what you think about that as well.